Good morning, everyone. Thanks for being here today. So the title of my presentation today is Interface Shear Transfer Mechanisms with GFRP-reinforcement. I am Camilo Vega from the University of Miami, and the other two researchers of this project, Professor DJ Belarbi from University of Houston and Professor Antonio Nani also from University of Miami. So this is the content that I have for my presentation today. First of all, I will make a brief description of the NCHRP project 12-121, which is the big project in these investigations. And then I will focus on the specific topic of my presentation, the shear friction mechanism, with the background, some context. Also, we will see some of the shear transfer design guidelines. Then I will define the project goal, and then I will pass through the experimental program of this project with the geometry, dimensions, reinforcement, the push-off test setup, results, analysis, and some conclusion. So let's get started with the NCHRP project 12-121. So this is the overall project of this research. The title of this project is Guidelines for the Design of Prestressed Concrete Bridge Girders Using FRP Auxiliary Reinforcement. It's funded by the National Cooperative Highway Research Program, and the whole research team of this investigation is composed of the University of Houston, the University of Miami, the Louisiana State University, and also Castrodale Engineering Consulting. And basically, the two main objectives of this project is to propose modification to the AASHTO FRP guidance specification for the design of prestressed concrete girders using FRP auxiliary reinforcement, and also to develop guidelines for the design of this type of girders using FRP auxiliary reinforcement. In this slide you can see a picture, and this picture shows a possible configuration of the auxiliary reinforcement that can be used in a typical prestressed concrete bridge girder. And the term auxiliary includes reinforcement that serves a wide range of purposes. So one of those purposes, and which is also the main topic of this presentation, is the reinforcement used in the shear friction mechanism. So now I will focus my presentation in that specific aspect. So regarding the shear friction mechanism, some background. In the context of reinforced concrete structures, when there is a need to transfer shear forces between components that may slide against each other, this transfer of forces typically happens along a plane. And this plane can be created by an existing or potential crack, an interface between different materials, a joint between two concrete sections casted at different times, also known as the cold joint condition, and also the interface between different cross-sectional elements, for example, the girder-deck connection in bridge constructions. So in the literature, this transfer of forces is known as the aggregate interlock mechanism, the shear friction mechanism, or interface shear transfer. And in general, the transfer of these shear forces is crucial for the effective performance of these connections. So the overall resistance of the shear friction mechanisms is based on these parameters: the mechanical interlocking and the adhesive bonding, the friction due to external compressive forces, the clamping force due to the reinforcement, and finally the double action of reinforcement. And based on these parameters, the current design guidelines for calculate the interface shear transfer capacity are based in two basic models. The first one is the shear friction model, and the second one is the cohesion plus friction model. So the first one is the easiest model. This model ignores the cohesion component and assumes that the transfer is due to the friction resulting from clamping force across the interface. And the second one, in addition to what is considered in the shear friction model, this second model does consider the contribution of the cohesive bond between concrete surface. So in this case, the resistance is due to the cohesion, the aggregate interlock, and the shear friction by force in the reinforcement. So we will talk a little bit more on these two models, and we will see some equations later. So this slide you can see the years since the interface shear transfer mechanism has been studied, about 6 decades, and here are some of the most important contributions on the topic. Nevertheless, in all this research has been one common factor, and that factor is the use of steel as a reinforcing material. So only in the last decades, a few of them have attempted to study the contribution of GFRP to the interface shear transfer capacity. So, as I said, all this research in interface shear transfer have served as the basis for establishing the current design code, especially when the steel is used. But when GFRP is used, there is a gap. Okay, so here we have two important codes and guidelines in the United States regarding the design of reinforced concrete structures using GFRP reinforcement, the ACI 440.11 version 2022, and the AASHTO BDS guideline for GFRP reinforced concrete, the second edition. And both documents refers to the shear friction mechanism in this way. So the first one, the ACI 440.11, mentioned in section 22.9, refers to shear friction as out of scope. And this code mentions that the shear friction is not covered in this code due to a lack of sufficient published research on shear friction in GFRP reinforced concrete members. So that means that this code does not consider the contribution of GFRP in interface shear transfer capacity. And on the other hand, we have the AASHTO BDS for GFRP, in this case, the second edition. Section 2.74 refers to interface shear reinforcement, but in this case, it mentions that for GFRP, reinforcement design shall comply with the provision of AASHTO BDS. So the point to highlight here is that this reference is for steel. So in this case, this guideline considers the contribution of GFRP in interface shear transfer capacity, but adopts the same principles as those of steel. So that means that based the calculation of the interface shear transfer capacity on the design tensile strength of the GFRP, even when the literature indicates that reinforcement doesn't reach this limit. So with this background, we identify a gap in the current regulations, and for that reason we perform this investigation. So let's talk about some of the shear transfer design guidelines. So in a previous slide I mentioned the parameters affecting the interface shear transfer capacity, and here are summarized the three main contributors of the capacity. So we have the concrete contributions, and this is represented by the cohesion or aggregate interlock. So depend on the surface roughness, the concrete type, if we have normal weight or lightweight concrete, the ratio of reinforcement crossing the interface. So because with this amount of reinforcement, we calculate the clamping force developed in the reinforcement, and finally any force perpendicular to the interface. So based on these parameters, the guidelines have established equation to calculate the interface shear transfer capacity. And only to mention a few of them, the ACI 318, the nominal shear resistance is given by this equation. This code is based on the first model, the shear friction model. It applies to steel reinforcement, and basically this is the equation. So ignores the cohesion component or the concrete contribution in the capacity. So let's see another one, the AASHTO BDS. In this case also applies to steel reinforcement. This guideline is based on the shear friction plus cohesion model, so for that reason you can see that this equation is longer than the previous one. In this case we have the contribution of concrete here, and in this part the contribution of the shear friction represented by the reinforcement, and also if there is any compressive external force. And finally, to mention the last one, the AASHTO BDS, but in this case for GFRP. So again applies to, in this case, GFRP. It's based on the shear friction plus cohesion models, and the equation is pretty similar to the previous one. So the only difference is the mechanical property of the material. So instead of Fy for steel, we have FFD for GFRP. So based on this background, or with this context, this is the project goal. So conduct an experimental assessment of shear transfer capacity of GFRP reinforcement using the push-off test, and also analyze and interpret the behavior of GFRP reinforcement in relation to the shear friction mechanism. So I'm going to talk about the experimental program. So tests were conducted to quantify the contribution of GFRP rebar to the interface shear transfer by using the push-off test. So in this picture you can see the overall geometry of the specimen. 18 specimens were built and tested. The general geometry, 16 inches wide, 32 inches height, and 8 inches wide. 8 inches thick. All the specimens were built with the same concrete strength capacity, 5,300 psi, and all these 18 specimens were built monolithically. So this is the reinforcement of the specimens. So 3 groups of the specimens were built, 6 specimens without reinforcement crossing the shear plane, as you can see on the picture on the left, 6 specimens with the steel stirrups crossing the shear plane. As you can see in the picture on the center, we use, in this case, stirrups number 4. So for steel, 2 stirrups number 4. And finally, 6 specimens with 3 GFRP stirrups number 4 crossing the shear plane, as you can see on the picture on the left, on the right, sorry. Basically, the amount of reinforcement in this case was obtained based on obtaining the same capacity or the same strength between the two specimens. So here you can see the amount of reinforcement in terms of area and reinforcement ratio. So this picture represents the push-off test. Basically, the push-off test is a compression test where a relative displacement, we want to create a relative displacement between the 2 blocks that conform the specimen, and this relative displacement is possible because of those gaps intentionally left during construction. So when we produce this vertical movement, the reinforcement that is crossing the shear plane, it's engaged in the phenomenon, in the mechanisms, and contribute in the interface shear transfer capacity. So regarding the instrumentation to record the strain and the measurements, we use LVDTs in vertical position to record the slip. We use potentiometers to record the horizontal deformation or the crack opening in this case. And also we use external and internal strain gauge to record the deformation or strain in the material. So external for concrete and internal in the stirrups crossing the shear plane. These are the mechanical properties of the GFRP rebar that we use. And just to keep in mind this value, because we are going to make a comparison later. The nominal ultimate tensile strength, almost 2% of that GFRP rebar. The tensile strain, the modulus of elasticity, and this one, the homogeneous for steel. Some of the results, so in this picture, on this chart, where you can see the slip versus the load. So the gray line represents the performance of the steel specimen. The blue line represents the performance of the GFRP, and the orange the performance of the unreinforced specimen. And in general, to highlight the contribution of GFRP reinforcement, going from 220 kilonewtons, sorry for the international unit, to 320 kilonewtons in the GFRP reinforcement. So we have a increase in the capacity in terms of maximum load and also in terms of deformation. Also, you can see that once the peak load in the GFRP specimen is reached, they have a drop in capacity, but then stabilize at a constant lower load, it's able to sustain that load and increase the amount of deformation. So a similar performance if we compare with the steel. So that means that GFRP is providing clamping restraint in that section. Compare the performance between steel and GFRP. You can see that in this case, the steel had a greater contribution compared with the GFRP reinforcement. But in this point, we want to highlight a key point, and this key point is the stiffness factor. And we can compare these two values. For the case of GFRP, this operation, the reinforcement ratio times the modulus of elasticity, is around 885 megapascal, and for the case of steel, it's almost 2 times, so almost 1900 megapascal. So that means that the interface shear capacity can be a function of the crack opening, and in that case, the modulus of elasticity could make a better interpretation of this phenomenon by focusing more on the stiffness factor rather than the strength. This chart shows the strain in the internal GFRP stirrup and load. And as you can see, at the beginning of the test, the contribution, or the main contribution to the interface shear transfer capacity is given by the concrete. So we have almost a vertical line because the strain increases at a very small rate compared with load. So that means that at the beginning the stirrups did not contribute to the interface shear transfer capacity. But once the cracking in concrete happens, the stirrup is engaged and starts to participate until the peak load is reached. And this point is, it's a key point because you can see that the peak load of the test was achieved at a value of a strain of 0.14%. So remember the maximum ultimate tensile strain in the test of 2%. So we are well below of the maximum tensile strain capacity of the GFRP. So regarding the failure modes, on the picture on the left, you can see the typical failure mode of the unreinforced specimens. In this case, we didn't have GFRP or reinforcement crossing the shear plane, so we have a sudden failure and brittle. But in the case of the reinforced specimen, either steel or GFRP, the contribution of the reinforcement to avoid the sudden failure were significant, so no sudden failure were observed in this case. And although some concrete spalling was observed in some of the specimens, the failure remained at the interface. This picture represents the typical failure mode for GFRP specimens. So again, the failure remains at the interface. No sudden failure were observed, and shear cracking mainly of the concrete and clamping and deformation of GFRP rivers. After testing, we performed inspection of the GFRP rivers. We found that no complete rupture of the cross-section area of the GFRP were observed. So finally, here we want to compare the experimental results with the design provisions. We are focused only on the GFRP results. So to calculate this, the theoretical capacity, we used AASHTO BDS, the second edition for GFRP. And you can see here that the experimental results for GFRP specimens are less than the estimate given by this specification. So according to the specification, the theoretical capacity, it's around 500 kilonewtons, or 112 kips. But in the experimental, we got these values. So if we perform the ratio between the experimental and theoretical results, this ratio is below 1. So this represents a warning from the point of view of safety and reliability in this case for this specification. So finally, some conclusions. So the GFRP reinforcement, in this case, the ratio of 1.42% confirmed the contribution to the interface shear transfer to values up to 47% higher than the ultimate strength capacity achieved in the unreinforced specimen. Once the ultimate strength is reached, the GFRP allows the specimen to deform, and this is very important, prevent the sudden failure. Also, the contribution of the steel to the shear interface resistance was greater than the contribution provided by GFRP. So this demonstrates that the actual parameters determining the capacity should go beyond the strength, and additional variables should be considered, like, for example, the modulus of elasticity, to consider the stiffness factor. And according to the last slide, you can see that the AASHTO provision were unconservative in estimating the interface shear capacity of the specimens reinforced with GFRP materials. And that's it, the acknowledgement for the Structural Material Center of the University of Miami, the CICI Center also, the NCHRP, who sponsor this research, OC, who also provide the stirrups to carry out this research. And thank you very much.
Doug Tomlinson, University of Alberta. Interesting stuff. Shear friction is definitely something to look into, because we want to change that clause 22.9 that says, so that's important. Just a question about your failure modes. You just saw that you didn't have rupture of the GFRP bars.
Yes, exactly.
Now, years ago I tested GFRP bars used for sandwich panels, so it's kind of like a little bit of an offset, but the same idea. But I saw, it's like kinking, and I saw like interlaminar, so the actual like resin between fiber layers had split, so you ended up having the system shifting. Okay. Did you see any of that?
No, we didn't identify that kind of failure in our test.
Okay.
As I mentioned, no, we make a inspection of the GFRP, but we didn't detect that condition.
Okay, and then second one, from Canada, so we always have to pull the Canadian things out there. That's just what we do up there. Did you look at the Canadian bridge code? Because there's some GFRP shear friction provisions in there, and they give like the C and U values.
Yeah, exactly. Indeed, the Canadian code has a stiffness approach, so because they consider the modulus of elasticity, and also they provide a limitation in the value of the strain to calculate the interface shear capacity. So that code, I mean, I didn't mention in this presentation because, as I mentioned at the beginning, the main objective of the research was focused on modify some AASHTO code. So for that reason, I used only that code. But yes, as you mentioned, the CSA S6 19 version, they provide an equation, and they have this stiffness approach, which is more conservative.
Okay, and lastly, do you have recommendations for the C and mu?
For what? Sorry.
For the shear friction, do you have any specific numerical or equations that you want?
Yes, exactly, because basically this part is just the experimental part of the project. Then we perform some numerical process of all this data, and in that process we are going to propose a new equation to include in the AASHTO provision, and also in the ACI 440.11. And obviously that equation, the approach of that equation, it's in the line of the stiffness factor. So we are going to include the modulus of elasticity, and also, as you see, one of the charts related with the maximum strain that we got in the peak load. So because the peak load is achieved in a small values of the strain, also we are going to have that limitation, even though it will be a little bit less than the current value of the Canadian standard, because in that case they provide 0.004, that is the maximum strain. So in our case, we want to propose around half, around 0.002.
Chuck handed me a mic, which is always scary. The stiffness approach is right. The Canadians are doing it right. Shear friction is always about stiffness. So if you want to get equal, you've got to do it with modular ratios. But what I don't understand is AASHTO already recognizes this. When AASHTO accepted 120 KSI steel, they limit the strain for shear friction to 002. Because everything is calibrated. Everything that we've done since Birkeland did this in 1960s is calibrated VC plus VS, and it's calibrated at essentially a 002 yield. So AASHTO's already doing this. So why aren't we recognizing what's already in the main LRFD?
No, but you know what? That, for example, we have this discussion with a guy from the FDOT who also works with all these things. And for example, they mentioned that they use AASHTO provision also to calculate this interface shear transfer capacity, but they never use, for example, the FFD value because of, all these results that we have obtained. So they always consider a small value of the tensile strain of the GFRP.
Yeah, you have to be careful because VC plus VS is wrong, right? Yes. VC peaks out very early and is falling. VS continues to go up, and we've decided at 002 we're going to add those two, and lo and behold, we get VC plus VS giving us a good number. So we've got to be really careful with this calibration. I agree that 002 seems to work if we're going to use VC, but we could change that by changing the C side, the concrete side as well. But this is in the main LRFD now when we went to higher strength steel, because it does go to a larger strain, obviously, with the same modulus.
Yes.
And it has to be limited because guess what? It doesn't work.
Oh, yes.
So
Yeah,
we're
no,
kind of
yeah.
reinventing the wheel here.
No, yes, exactly.
Dr. Carloni was next. Oh, did I get the wrong order?
I think, yeah. But thank you so much for the presentation. A couple of questions. The first one is, your curves show that you have the same slope of the three tests: concrete, steel, and GFRP. That's something that I would have not expected, that there's no change of the slope. Because it's not possible that you continue to have the same stiffness of the three responses. The other thing is, and I'm not a designer, so I think I'm probably off here, but so I'm not sure what this kind of phenomenon we're trying to focus on, because if it's a shear crack, there's going to be an opening that is opening with a different amount through the line. If you're talking about dowel, it's two materials, and so you should consider the effect of the two materials. But even more importantly, why we're looking at the elastic modulus and not at the shear modulus? So why we're looking at comparison of the elastic modulus times rho when it's a matter of shear? I'm confused.
Oh, okay, so let me respond the second question first. So in the second question, you say that we should consider the shear modulus in the contribution of the shear friction capacity, more or less. Yeah, okay. So what we need to keep in mind, for example, at the beginning of the presentation, I mentioned the different parameters that contribute to the interface shear transfer capacity, and one of those parameters is the dowel action. That's great. But in this phenomenon, we need to take into account something, and that all the parameters that contribute to the interface shear transfer capacity don't provide the maximum contribution at the same level of slip. So, for example, the dowel action or the maximum contribution of the dowel action appears when the peak load of the test has already been achieved. So, for example, when we have this curve, in this part, when we have larger values of slip, the contribution of the dowel action start to participate in the phenomenon. But in this point, we already have achieved the peak load. For that reason, the most of the design guidelines do not consider the contribution of dowel action in the calculation of the interface shear transfer capacity. Yeah, that answered your question, or? I mean, we need to take into account that when we perform this test, the maximum contribution is due to the clamping force provided by the reinforcement. So the slip, when we apply that load, there is a slip, but also that slip produces a crack opening. When that crack opening happens in a perpendicular direction, engage the reinforcement, and the reinforcement work mainly in tension. Exactly. Yes, exactly. Because I mean the capacity is being resisted by friction for the reinforcement. So I got your point because if you.
Yeah, I think it's a good point. I think we'd like to get some other questions in before we go. So.
Okay. Okay, bueno. I mean, we need to. No, because you mentioned at least, no, because at the beginning, the contribution is mainly for the concrete. Exactly. In this part, it's pretty similar, yes. Okay. Okay, yes. Mm-hmm. Yes, exactly. Thank you.
But let's get another opinion here. Unfortunately, we have a lot of time, so that's why we're
Excellent work, Camilo, as usual. I'm Ayman Okil from Louisiana State University. My question to you is, are you planning to expand on this and see what the behavior that you are finding out is going to reflect into the design of big structures? Like, is it going to be controlled by vertical shear or horizontal shear, the amount of stirrups that you will need in a member? Is this something that you're planning to study?
Yes, exactly. Actually, I mean, we perform this test because it's a simpler test if we compare, for example, with a test, a composite beam, for example, a girdle connection. But yeah, the idea now is transfer this information to a bigger, example of this. For example, the girdle connection. So we are going to perform some calculation for this application, for this special application. Yeah, that's the idea.
Excellent presentation. John Myers, Missouri S&T, and you're up next. Real quick question. So forward looking, in terms of shear friction, are you going to look at cold joint testing across that plane? So if you have an element and then you have different surface roughening,
yes,
pouring concrete on top of that, and then also, do you think if you dowel an epoxy into one side of the cross plane, if that would have any influence on the test results?
Okay. Yeah, indeed, this result that I am presenting today is just the first phase of the project. So in the second phase, we perform additional tests using the cold joint conditions in order to study the performance of the GFRP, mainly post-cracking behavior. So in those results, we have seen that the performance of the GFRP, or the contribution of GFRP is affected by the cold joint, so it is reduced a little bit. But I mean, the behavior is, in general, if we have or not the cold joint condition, the contribution to increase the capacity is important. So, yeah, exactly. In that case, the size of the crack are bigger in that case. And regarding the second question, that if we use epoxy to, exactly. Also that is going to affect the contribution. Yes, definitely.
Great job. Thank you very much. I actually have a huge interest in this topic because we're working with the Ministry of Transportation of Ontario, and I don't know if Mariana is here, University of Waterloo, exact same test. Going back to what Christian mentioned, we're not seeing exact same curve in the same test we're doing. Since you have increased the number of the reinforcement, you have already increased the stiffness, and that picture I see is more like you're transferring the shear into finally a bond failure, because now the slippage, so we're seeing a slippage issue, which the bond strength of the bars are, counting. So that number one, and again, funny, everything related to GFRP comes back to modulus of elasticity. The sky is falling. It's the modulus of elasticity, which I don't think it has anything to do. But the number one question I have is, how did you create the shear friction surface? Because the test we are having is, typically they do this by a sand blasting process. So you make a concrete and another concrete. You have a bridge deck, and you want to put bridge barriers, and they grab sand blasters, and they start sand blasting the surface. If you have created that shear friction by a sand blasting process, or were these two casted at the same time, or was the sand blasting used, and how do you know the sand blasting did not damage the bars?
Okay.
Yeah, exactly. That's.
Yeah, exactly. No, yeah, but it was almost similar to that question of Professor Mayer. So in this case, these results are just for monolithically cast specimens. So this result does not consider the cold joint condition. Yeah. But as I mentioned, we perform also another test with cold joint condition, and definitely that the cold joint condition affects the performance of GFRP in the interface shear transfer capacity.
Thank you. Your dissertation.